Relaxation. So I'll not work out the algebra details. I'll mention some prominent steps, and then finally those, at least a lot of it is already here. So this I'll share at some point, so if you're interested, and it's available in books and all that. So one approach is it's called red field theory. So where you have these nuclear spins, so that's some small quantum system, and then it's weakly coupled to a bath. Bath are the, in our case, the electronic spins, and so Hamiltonian has a time-independent part H0. Okay, forget the RF field and all that. All that is gone now. Okay, you are looking at something is been excited, then how does it relax? So from your side, it's only the Zeeman part which is always there, and then you have this time-dependent part in the Hamiltonian. These are the fluctuations. So you have these electron spins which are doing something, and that is part of this H1. The H0 is just the Zeeman term, and the H1 contains the fluctuations. And how is that going to drive relaxation? So this H0 is of course just minus gamma nuclear H bar I dot field. Yeah. So while this H1, it contains a fluctuating field, so it is both. So you have the nuclear part dot whatever is the field. So nuclear moment and then field due to the electron spin moments, and those are fluctuating. So that is creating the time dependence. Then there are some assumptions that you assume weak coupling between the, so you have so nuclear spins is your system, and your bath is the electron spins, and they are weakly coupled, and then there are some standard assumptions. So then so you have these various electron spins in the bath, and at least when you initially derive it, there are only weak correlations between the spins of the bath. Okay, so these moments are fluctuating very fast, and so the correlation times are short. Later, of course, you'll look at antiferrocorrelated moments and all, how that impacts. But to start with, so you have between the system and the bath, you have weak coupling, and even within the spins of the bath, you have weak correlations. And another assumption is that so I mean, one is treating this in the so-called weak collision, strong collision regime, where there is no memory of what happened at the previous. So these are fluctuating so fast that it's as if you are having very fast collisions, and there is memory loss of what happened earlier. This is how you treat brood model, etc. in the beginning. So anyway, once these starting points are defined, then again, I'm not going to work out the detail here. So the starting point is that you work with the density matrix. So right, d rho by dt is minus I by h bar, commutator of h with Hamiltonian with rho. Okay, and basically you are concerned with the time dependent part. So this is going to be minus I by h bar, and this is time dependent part and time dependent part density matrix. Okay. Again, this is not immediately we're not going to work out the details, but so in quantum mechanics, you have this Schrodinger picture where all the time dependence is in the wave functions, right? And then there's this Heisenberg picture where all the time dependence is put in the operators. And you write similar equations anyway. And sort of in between is something called the interaction picture, where part of the Hamiltonian it has the time, part of the operator has time dependence, part of it is there has a time dependence in the wave function. So here this is treated in the interaction picture, where you can think the wave function evolution being governed by the Zeeman term, so e to the power minus iet by h bar sort of thing, and the h1 part as a part of the operator time dependence. So that's loosely what is done, and then what is done is symbolically you can think about integrating this. So you will get some at t equal to 0 or something plus some integral, and some algebra, you work through it, and what you get is, again, we are not going to get bogged down by the details here. I'll write finally what's obtained, which is useful for us. Directly we can use it. So one can expand to second order in H1, and one gets 0 to infinity integral, where you're looking at basically what these fluctuations are doing. Okay, you have a commutator of H1 and another commutator at a different time. Okay, you can write this if you like, otherwise you don't have to even write it. Another square bracket, and so it's very loosely, it's obtained by doing one integral, then you get rho, put that back into the first equation, right? You think about doing one integral, so you get something for rho, put that back over here, and then, with a little bit of effort, you get this. So how the density matrix?
The full Hamiltonian, if we put it back to the first equation? Or we just consider that?
Yeah, so we are just considering the time dependent part. So again, in the interaction picture, you keep the time dependent part in the operator corresponding to the H1.
Right.
So finally it's only the H1 that contributes to these changes.
But aren't they the same equations then? Like if it is only the time dependent part, the first and the second in the previous slide, aren't they the same equation?
These two are the same. Yeah. This is generic. Now we are writing it in the interaction picture, and then you have to sort of solve this.
So we do it self-consistently, something like that?
Something like that. Yeah. So you integrate, then put it back in here, and something like that. But some details are there in the next couple of pages. So. Okay, and then. So sorry, I skipped some detail, but this I'll provide otherwise. And at the end of it, right? So at the end of it, what you get is 1 over T1. You write down what the time-dependent Hamiltonian is and so on. What you get is 1 over T1 is, with the correct three factor, etc. So this is the nuclear gyromagnetic ratio, gamma n square by 2. The integral of H plus at t and H minus 0 e to the I omega naught t dt. I'll quickly tell you how you can get just this. I'm missing. So you are going to have terms like, just write it anyway. So this H1 has the nuclear I, as also the H due to the electron spins, okay, in dot product. So you are going to have things like Ix, Hx, Iy, Hy, Iz, Hz. Okay, then the usual logic, if you want to cause transitions, so you want the fluctuations or the transitions in the electronic system be coupled to some transitions in the nuclear part, right? So it's only, so the Ix, Hx and Iy, Hy you write in terms of the plus minus. And it's only those that are going to contribute to these transitions and to the relaxation per se. Okay, so this H1 is just minus gamma H bar, and then as I said, Ix Hxt plus Iy Hy plus Iz Hzt. You smell smoke now, maybe something burning outside or something. This side. The ducts, huh? It smells more like some wood or some kachra burning. So this one can be write as gamma and H bar minus, and then this is written as half I plus H minus plus I minus H plus plus Iz Hz. So where this, in general, this Ht is the fluctuating, in our case, fluctuating electronic field, magnetic field. And then this I plus T, for example, is, so there is a time independent part, and then we have the e to the I omega naught T. And similarly I minus, and Iz is just Iz. Okay.
So these are the nuclear spins, right?
I are the nuclear spins, yes.
And H is the Zeeman field that was.
No, Zeeman is there, so that's part of this omega naught. You have the bath which contains these electrons, which are fluctuating. So it's the field produced by these electrons through the hyperfine coupling. So we usually write this H as some A times spin. So you have an electron spin which is giving rise to a field, and those spins are fluctuating, so it's giving rise to a fluctuating field. And it couples to the nucleus by this A, prefactor hyperfine coupling. So that is not explicitly written here. If you want to now write it in terms of the, so right now, therefore we don't have a, in our answer, we don't have a so-called hyperfine coupling here yet. But once you write H in terms of, rather than H plus H minus, you write in terms of the S plus S minus, then you will pick up a square. Okay, so the relaxation arises from fluctuating electron magnetic fields. Okay, and of course only the transverse component, right? The others, the Z component doesn't contribute to relaxation. So one writes these in this form, and then the H1 one puts it back in that first equation where you have to find the commutators and so on. And okay, let me what form to write it. Somewhere written in terms of the spins also, but okay, we'll just write it one by one. So incidentally, this quantity, this integral, so integral minus infinity to infinity, written t prime, but it doesn't matter, dt e to the I omega naught t h plus t h minus 0. So this is of course the field correlation function, you know, at t equal to 0, what is the field, how that correlates at some different time. And this is spectral density function. So what kind of contribution do the fluctuating fields have at the NMR frequency? That is what will finally drive the relaxation. Okay, so I have in terms of the spins also somewhere. So just to okay, I've written it later in terms of the spin operator, so I'll yeah, I'll bring that up a bit later. So incidentally, I mean, you finally in your calculation will have both terms, h plus h minus and h minus h plus also. Okay, so the total 1 over T1 is actually combination of both, and since these two are equal, we finally just put them together in one equation. So if you want to write bit in detail, it's actually so even written like this. So you write 1 over T1 as a combination of, so then gamma n square by 4, and then integrate over all times, and then you have both the correlations, so e to the I omega naught t, and you have a h minus t h plus 0, and plus another term e to the minus I omega naught t, or in my notation here it should be this should be minus, but doesn't matter finally. H plus t h minus 0. Okay, and then each, so this one can be written as j plus minus omega, omega naught really, we are using this at the NMR frequency, and likewise this second one as ulta, j minus plus omega naught. And then these are equal, so you can just combine them in one and you get this finally gamma square by 2 and one of the integrals. So this is, there's this red field picture where you start with this Liouville equation, d rho by dt is I bar minus I by h bar, commutator of h with rho. Work through it and obtain the relaxation rate, which is related to time dependence of the density matrix. This is one approach, and you generically get this, that the rate is dependent on the spectral function of this fluctuating fields. Okay, because you have these spins fluctuating, there is some frequency dependence, but really the component at the NMR frequency is what will contribute to the relaxation. The other approach is just using Fermi-Golden rule. You have perturbation in H1, and that gives rise to, so you have a transition rate which is given by square of the matrix element and so on. Okay, so, and of course that also leads to the same result. So very quickly we can at least write down. So this can be done also, and it leads to the same result. Okay, so you are looking at transition rate, and that's related to square of the matrix element, 2 pi by h bar square of the matrix element. There are different ways of writing that also, and so you put the h1, which is time dependent, and then you get back, of course, the same result. Now, in general, you write, so if you have energy levels, Zeeman levels identified by this m, some quantum number m, then, and this Pm, it's like a probability, but it's a population of mth level. Okay, and this W, let's say m to m plus 1, is of course transition probability per unit time. Okay, so of course it's easy to do first the spin half, but in general you can write that how does the population of the mth level change? Well, you have m minus 1, m plus 1, and so population will increase because of m plus 1 going to m and m minus 1 going to m. So it depends on the population of the p m plus 1, so p m plus 1 times w m plus 1 to m. Similarly, you have to add p m minus 1 and w m minus 1 to m. Okay, but likewise you have the other way also. You are depleting the m by some transition from m to m plus 1 or m to m minus 1. So with a minus sign you must take into account those also, right? So in general you will write this is equal to sum over some index m prime w m prime to m multiplied by p m prime, and minus, so this is something coming into m from m prime. So the population in m prime multiplied by the rate that it's exiting m prime. Okay, that's adding to the mth level, right? Transition is to m, so that comes with a positive sign. On the other hand, something which is leaving m will come with a negative sign. So you have w m to m prime, right? So it is leaving m and going to other levels, and of course pm. Okay, so whatever population you have in the mth level multiplied by this transition rate, probability per unit time, so that comes with a minus sign. So simplest case is to do it for spin half, so that only 2 levels, okay, and then you can also then rewrite this in P plus and P minus. You know, you can identify your levels as 2 levels, say, whichever way, you know, which way did I write it, I don't know, but okay. So there are 2 levels, so population of this level is P plus and population of the other is P minus, and likewise the transitions will be like W minus to plus and so on, okay, and so one can write down, so for this 2 level system, dP plus dt is of course minus W plus minus P plus and plus W minus plus P minus, right? So you're looking at rate of change of population of plus level. So whatever is the population here multiplied by so the decrease involves what is exiting the plus level, so that's the population of the plus level multiplied by the rate at which it is going from plus to minus. There are only 2 levels. On the other hand, there is an addition because you have something in the P minus, in the minus level, and then it's transiting from minus to plus, so that's adding to it. So you have just these 2 terms. Likewise, you can write dP minus dt as minus W minus plus with P minus and plus W plus minus with P plus. You know, in a measurement, you're finally interested in what is dmz dt. Okay, so you can basically multiply by so mz is just gamma h bar by 2 P plus minus P minus. Okay, you're dealing with spin halves, nuclei, okay, and the difference of the population of the 2 levels is what gives the magnetization. So you can look at rate of change of magnetization by looking at this rate of change of population based on some general detailed balance principle. Okay. One can similarly do for spin 3 half also, but then you'll have 4 levels, and accordingly, depending on what the initial conditions, you'll have more terms. That be important when you derive the 1 over T1. You know, in this case, it's just exponential, simple. But for spin 3 half in a quadrupolar situation, you'll have 2 exponential. So work it this way, it's important at that point. Okay, so one can write rate of change of magnetization also. And so magnetization changes with time, and in the end, you will have a steady state. So so dmz by dt will go to 0. Okay, so one can, in equilibrium, what are the populations? You can write that by, you have P plus minus P minus, you can write that from here, dP plus minus d, so that will give you dm by dt, and at t equal to infinity, you have equilibrium populations, and so that will actually give you that W minus plus P minus equilibrium equals W plus minus P plus equilibrium. So as t goes to infinity, the populations are of course changing, and at t equal to infinity, the dm by dt is 0. So when you work out d from these 2 equations, dp plus minus dp minus by dt, and then just combine these, and that should go to 0 at t equal to infinity, and p should be p equilibrium, p plus p minus. So that will give you that this is how the rates are connected. They're not equal. Okay, that's why I mean all the physics stuff works out. You have the Boltzmann factor, and that's what determines the ratio. So what is ratio of P plus equilibrium by P minus equilibrium? Boltzmann factor, e to the minus delta E by kT. So the two rates, plus to minus and minus to plus, are not equal. They are different due to the Boltzmann factor, and that's why you have a population difference. That's why all the physics rest of it. So anyway, because of this, what is the net, equilibrium level. What is, you will know P plus equilibrium minus P minus equilibrium. That you can write down. So that's your, in equilibrium, what is the net nuclear magnetization? So one usually defines 1 over T1 as W plus minus plus W minus plus.
So just one request. Actually, in the PDF, this thing cuts out. Okay.
Oh, is that right?
Yeah.
Oh, wait. This goes. Of course, no. This goes to the next page. Yeah. Good point. Yeah. So here, of course, it's convenient to write. It's sort of one single board. Yeah. So yeah, I can stick to this part. So you have a W minus plus P minus equilibrium is W plus minus P plus equilibrium, and again reminding you that the ratio P plus P minus at equilibrium is given by the Boltzmann factor, e to the minus delta E by kT. So remember, which way is positive, negative, which is higher, lower? In our scheme, P plus is the more occupied at the lower level. So more population in the lower level. You have a thermal excitation, so you have less, and the ratio is, so upper to lower, right? So P minus by P plus, under equilibrium condition, is e to the minus delta E by kT. Okay. And in general then, this 1 over T1 is written as W plus minus plus W minus plus, and look, usual situations very close to 1, the ratio. So this is finally also written as 2W, okay, twice the transition rate.
Sir, so is this the, what is known as the principle of detailed balance?
That is the principle of detailed balance, this one here. Writing this is principle of detailed balance. So you're just applying principle of detailed balance and then connecting that to what the actual nuclear magnetization is and how the magnetization should then relax.
This is exactly how, in a classical spin model, one models the spin fluctuations. Like in an Isaac model,
Yeah.
Metropolis algorithm is exactly.
I see. Okay, so based on what temperature you are, you accordingly give probabilities to occupation and all that. They're driven by the Boltzmann factor. Yeah, so one can, again, with some notation I'll write down. So, gamma n h bar by 2, the half comes because of the spin half of nucleus. We are looking at spin half. If you had electronic gamma, then of course GE by 2 mc. So G equal to 2, then you get back the Bohr magneton. Okay, but this is not, this is some nuclear magneton. So anyway, so the half is there because of the spin half of the nucleus. Okay, so gamma n h bar by 2, P plus minus P minus. So this is mz, and gamma n h bar by 2, P plus plus. You can think of P plus, P minus also as probabilities. Though I called it population, I say 1, population, total population 1. So this is actually equal to gamma n h bar by 2. Some of the probabilities is 1. Okay, so if I now put these conditions, okay, I wrote slightly bad notation maybe, but I'll just stick to it. So if I take this population difference as, sorry, this m is used in different contexts also. Okay, maybe I can change here. I mean, my note says m, but mu, yeah, mu is okay. And of course the other one, P plus plus P minus is 1. We have said total population 1. Okay, so if you do this and then you can write dm by dt, right? Because you have dp plus by dt, dp minus by dt. So the difference of the two will give you d mu, which is related to finally mz through a gamma h bar by 2, this one. So you can write dmz by dt on the left hand side. And the right hand side by using, so right hand side what will you get? So difference of equation 1 and 2, right? This is equation 1, equation 2. So you get the difference of these. So you can, with little bit of effort, so I mean it's just some algebra. So you have W minus W plus minus P plus, and again another minus W plus minus P plus, and so on. So again, if you work through the algebra, the d mz dt works out to minus mz minus m naught by t1. Okay, because we have defined what these mz and m naught are. M naught is when you look at equilibrium populations. Then on the right hand side you'll get m naught. We have defined it like that. In general, mz is at any time p plus minus p minus multiplied by gamma h bar by 2, that is mz. Okay, so if I put instead p plus equilibrium minus p minus equilibrium, then what I'll get is m naught. Okay, so the right hand side there I can write in terms of mz m naught. Okay, by just making use of these things, and I get the recovery of nuclear magnetization in this manner. Okay, so this is the reason why we get finally, when you are looking at nuclear magnetization recovery, you have this exponential, right? From here you can solve for mz, and so right, so something like that. So depending on what your initial condition is, okay, if you start out with the initial condition that mz is 0, and then how it evolves, you get it by this equation, where remember this 1 over t1 is our definition, w plus minus plus w minus plus, often written as 2w. These are almost the same, but of course they are not identical. So if you now have to work out the recovery equation for spin 3/2, this was a simple situation, two level system. In practice, we work on nuclei spin 1 or spin 3/2, etc. So if, for example, spin 3/2, if this I'll do later. So energy level scheme, if you have spin 3/2, then it is 3/2, half, minus half, minus 3. Okay. Now, if you have only the Zeeman term in the Hamiltonian, in the sense the time dependent part, that is different. Forget about that. But otherwise, if you have only the Zeeman term, then there is no issue. You have all these energy levels equal, and when you look at the resonance spectrum, you just get one single line like this. Okay, and then the recovery law is still the same. You can again work out, by the way. Okay, with whatever initial condition you choose, that you kill totally the magnetization by your initial pi volt 2 pulse or whatever it is, and these are energy levels are equal. So again, detailed balance. You have now 4 levels. So m runs from maybe 3/2, half, minus 3/2. You can put that as the label. And then dp, half by dt, can be written in terms of the transition rates multiplied by the population, so on. You can work out. So if you have really the same energy level spacing, you'll get back the simple exponential single T1 variation. The interesting situation arises when, in addition to the Zeeman, so this I'll do a bit later in the detail of it, you also have a, so remember this is spin 3/2, so this is not a spherically symmetric nucleus, the charge part we are saying, so it has a electric quadrupole moment. Okay, so you have a Zeeman term, of course, but then you can again consider different limits. So large Zeeman and a small quadrupolar term in the Hamiltonian. So what is happening? The nucleus is no more spherical as far as the charge distribution goes. It's not spin half. And as you know, if you look at a multipole expansion of some charge distribution rho, then the dipole part couples with the electric dipole part couples with the electric field. Okay. So the quadrupole moment couples with the gradient of the electric field. Okay. And so on, I mean higher order terms. Okay. So if you just consider the order of where the quadrupolar, so the quadrupole moment couples with the electric field gradient. So if you have a, so you're not looking at the nucleus in isolation. It's part of a solid. Okay. So there is a possibility of having an electric field gradient. You know, you have ions at various sites, so they give rise to an electric field, but also they might give a gradient of the electric field. If it's a non-cubic symmetry site, they might give a rise to a gradient of the electric field. Then that couples to the quadrupole, electric quadrupole moment. And you have an additional term in the Hamiltonian. Okay, the details I'll work out at some point, but the final effect is that, again in first order, where this is weak compared to the Zeeman, so this is called the central line. That doesn't change. I mean, each of them shifts, but this remains the same as before, as when you did not have the quadrupolar term in first order. The other one shifts depending on, again, this detail I'll write down a bit later, maybe 2 classes from now. So you have an electric field gradient, and you can write in terms of the second derivative of the potential. Okay, you can choose some principal axes where Vzz is del square V del Z square. Okay, similarly you have Vxx Vyy. Okay, the convention is that the component which is the maximum, that is called Vzz. Okay, that's the convention. That's the corresponding Z axis. So wherever the maximum of the electric field gradient is pointing, and the direction of the magnetic field with respect to this direction of Vzz, that will, because that's how the Hamiltonian comes out, there's an angle involved between the applied field, which is the Zeeman term, and Vzz, as to what the energy spacing will be. Okay, so it depends where the applied field is either parallel to this specific Z axis or perpendicular, and of course you can have anything in between if you have a powder pattern. So in one situation you will have something like this, the energy level spacing. Okay, both these minus 3/2 and plus 3/2 move down. Okay, as a result, now you have, so whatever this comes down by, this goes down by the same amount. So whatever this decreases, this increases by the same amount. By the way, it's not looking like that, but that's how it is. So instead of a single energy level spacing, you have now 3. So in the simplest case, first order and specific angle, the central line doesn't change. it remains at the same resonance frequency. But now you have two more resonance, one on this side, again schematically, one on this side. The higher one corresponding to this higher frequency, smaller one corresponding to this frequency. So this one is called the central line. These other two go by the name of quadrupolar satellites.
So these satellites need not be symmetric. They should be symmetric.
They have to be symmetric. That's how the equations work out.
But in the intensity can vary.
No. So that's a separate calculation. What are the relative intensities of these two satellites? They'll also be the same. Now the position of the satellite changes as you change the angle of S0 VZZ. So if you could have a single crystal and you could vary, so applied field always remains the same. You have some big setup solenoid, but the crystal you can rotate. Then this will move in this direction, go to one end and move and so forth. So in reality, if you have a powder sample, you'll get some overall average of that, angular average of that. So anyway, this detailed part I'll do at some point. Here what we want to say is that when you're looking at now relaxation of a quadrupolar nucleus where this is the spectrum, then it is not a simple single exponential. Again, you have to apply detailed balance and all, and you have to, let's say you specify a condition where with the initial pulse you saturate only the central line. You have limited spectral width, remember I said? So you might have limited spectral width and these may be out of your window of observation. So you irradiate only the central line and then you want to look at how the magnetization relaxes back. Okay, so again one can work this out where you have only magnetic relaxation, so only the fluctuating fields are contributing by writing those equations and putting the suitable initial conditions. So you can work this out. By the way, I found you give this problem to ChatGPT, it works out also correctly. You can do it tells you 3-4 different ways to do it. You can do spin 5/2, 7/2. It gets more and more complicated. 3/2 is the simplest. Okay, so you can use that also. So magnetic fluctuations, ask it spin 3/2. So relaxation rate in the presence of magnetic fluctuations when only the central line is irradiated. Okay, and then see how it works out. Then you can sort of quiz it and you can also learn what happens at different steps. Okay, so the final upshot of all this is that the relaxation in the case of, let's say, spin 3/2 nucleus is no more 1 minus e to the minus t by t1. Okay, it looks more like, and in the special condition of only the central line being irradiated, the answer looks like mz equals m0 1 minus 0.9 e to the minus, I think this one is, so the faster rate 12 wt minus 0.1 e to the minus 2 wt. There are other different initial conditions which will lead to different coefficients, but you'll always have only a 2w and a 12w.
This is for 3/2.
This was spin 3/2, where you are able to irradiate only the central line and the satellites are out, and you're looking at relaxation from magnetic fluctuation. But I'll do this at some point, and ChatGPT does it also quite correctly.
So suppose we have this quadrupolar nuclei. Do we also irritate the satellites also?
But it depends, no? Suppose this is 10 megahertz and your spectral width is a little bit, not that much, it's only less, then there's no way to irradiate. Suppose this is close.
You just want to get the spectra, then only we are irradiating.
Sir, he's asking probably if the satellite peaks are not far away,
If they're inside, then usually you are able to irradiate, then you get a single exponential, then there's no issue, you are back to the old. If you're able to irradiate all of them in one go, then you get a single exponential.
Physics point of view, when we are irradiating central, we extract this T1 and all. So can we do that for satellite also?
Separately, only the satellite, of course. So again, you have to go to detailed balance equation, and so let's say this corresponds to only plus 3/2 plus half transition.
Then
So in isolation, yeah, one can work that
So
out.
That
overall
will-
physics of the system will remain same. Either we irradiate the satellite or central peak.
Yeah, your recovery thing may be different. Or you can also, suppose your nu q, that's the quadrupolar frequency. Let's say it's something like 30 megahertz. It happens many copper-based systems which has a large quadrupole moment. So 0 Zeeman, you don't need to apply a field. Okay, copper 63, copper 65, both are spin 3/2. So what are the energy levels if you have no applied field?
I don't know.
Spin 3/2 nucleus. There is no Zeeman, there is no applied field H0.
Half, I do.
What are the energy levels? Only quadrupole. EFG is there.
So all four will be there.
No.
There's no Zeeman.
No,
Degenerate.
minus
There
plus
should be
nine only.
degenerate.
Yeah.
You will get 3/2.5 only. Right?
Plus minus 3/2 degenerate, plus minus half degenerate. So you'll get only two levels.
3/2.5.
Right? And so you can do a pure NQR experiment. It's called nuclear quadrupole resonance. You don't need applied field. You just do this experiment and find out nu q. Now this difference is proportional to the quadrupole frequency basically. It depends only on the quadrupolar term, there's no Zeeman term here. One can do a pure quadrupole experiment, and one can do a T1 measurement here. And what's the recovery law? It's only a two-level system, so of course it's exponential.
This is only possible for copper.
Nothing like that. It depends on the nucleus. If the nu q is large,
Okay.
it depends, no? I mean, it may be 1 megahertz. Is your spectrometer able to? Are you able to do? Once again, this idea of Boltzmann factor, e to the minus delta E by kt. If this is very small, then you may not have enough, sensitivity to detect the signal. So typically, less than 10 megahertz is not so simple. So chlorine you can measure pure NQR. So nothing of that sort.
Sir, but one can also maybe bring the satellites into our range.
Yes.
Because H0 is something
Yes.
which we reduce, right?
So if it is sort of within your technical capability, you can use pulses so that you irradiate the full thing. Then there's no problem of, fitting to multi-exponential is always tricky. Once you are sure it's single exponential, straight line and some log plot, there is no confusion. Agreed. So to the extent possible, we should try to irradiate everything. Then you'll get single exponential, you obtain the T1.
But we need to rotate the sample in that sense because H0 we need to.
No. Suppose you are doing not rotate. Let's say you're doing a powder sample, not even a crystal. Then actually as I said, this explains some other time, but so schematically, the spectrum for spin 3/2 looks like this. Okay, there's also a specific ratio, I think 3:4:3 or something. So these are called a powder pattern. Because you have now different crystallites which are at different angles with respect to the applied field, random. So you have to do an angular average, and that's what gives you this. And of course, you have more directions perpendicular than parallel. Only one in the angular average. You have only one possibility of. So this arises from the parallel, and this arises from the perpendicular. So actually, if you want to write out what the individual, so just the plus 3/2, plus half transition, that one is like this. So for that transition in the parallel orientation, it's actually on this side, and in the perpendicular orientation, it's here. And similarly, the -half, -3/2, you will have again. You will have a like this, like so. And if I remember correctly, this is 2 nu q or nu q?
2 nu.
Maybe 2 nu q. And then between here and here is another nu q. Okay. between these, so these go by the name of step. Okay, it's not always easy to say step. This is called a singularity. So that's just the nomenclature. So from the singularity to the step is nu q. From the singularity to the central line is another nu q. So between the two steps, it is 4 nu q. For spin 3R. Huh? If you have spin 5R, you will have again larger number of satellites, depending on the number of transitions possible. You are allowing only for delta m equal to plus minus 1 transition, of course, only magnetic selection rules. Okay, so the powder, so if you could do a single crystal, then you will get 3 lines, but the location of this will be only unique, you will just get sharp line, and the distance depends on your angle.
This is for a powder sample.
The yellow one is for a powder sample, yeah, which is now averaging the red one. So central line of course remains the same, and you're just averaging all of that, and that's generating the powder pattern. What were we saying? Yeah, so if you could irradiate the full thing, of course that's great, and then you get easily by just exponential fit T1. So one point about which is made that in NMR you always measure inner field. So you're not measuring ground state in that sense. No, you want T equal to 0, nothing else, H equal to 0, no. So in that sense, if it's a quadrupolar nucleus, then this is a zero field measurement. Okay, so it's really ground state. So if you could measure T1, just a quadrupolar, between the quadrupolar levels, so plus minus half, plus minus 3 half, then you're measuring really ground state. Pure quadrupolar. You can have different situations where this dominates and the Zeeman is small. So this is the main term, this is the perturbation. In between, you cannot solve exactly. Okay, so it's all done in detail for many situations now. Right. So we were actually just looking at T1s and
तो highest nu q कितना देखा गया? I mean above 30 megahertz is common or it's kind of rare?
no, not so rare.
Not so rare.
Not so rare. I mean, in high TC cuprates, you have two kinds of copper at the chain side, copper at the plane side. And it was like 30, 20 something and 30 megahertz, so not so uncommon. I think then chlorine is also, it has a strong quadrupole moment. So chlorine also pure and pure, you can see. Zero field. You need something at where there's electric field gradient present.
That
So
zero field, we have seen one paper, no? I think Bennett circa
Ah.
about alpha RUCL.
Yeah.
He written zero field NMR.
So they're talking about this alpha ruthenium chloride, which is said to be Kitaev quantum spin liquid. Problem is, it actually orders, the Heisenberg term is not 0. So it orders at 8 Kelvin. But with the application of about 8 Tesla, you can totally suppress the Heisenberg part. And there's no more ordering, and then they say the excitations seem to have features of Kitaev. Majorana, fermions and all that. So there a lot of NMR has been done. Chlorine is the good nucleus there. So 35 chlorine NMR and QR has been done. Of course, you need to do NMR in a field 8 Tesla to kill the ordering and then look at things which arise from this Majorana.
So these excitations we should capture by INS. So INS में भी field apply होता है? हमें इसका idea नहीं है.
In general, INS you don't apply a field.
But
You might
can
want
we
to do
apply?
it with a field.
Can we apply?
It depends on the places. Now, yeah, you can apply.
Field depends.
Because alpha RUCL3 में अगर उनको Majorana fermions scan
हाँ,
करना है,
हाँ,
they have
People did
to.
No, but they say even above the ordering, you can see features associated with
Okay.
these quasi-particles.
I think INS was done in field for alpha RUCL. It is 9 Tesla, 20 Tesla. Then they find some continuum shape below 1 or 2 Tesla.
Yeah, it
they
was
have
done.
seen
Yeah,
this
yeah.
speed
So you
wave.
need your beamline spectrometer to be capable of doing that, to be able to apply 8 Tesla, 9 Tesla variable field.
In one of the papers,
Yeah,
there's
yeah,
this
yeah.
spin wave shown, and then 9 Tesla, this continuum.
Yeah. So the Heisenberg part, the ordered one will give spin waves. Now once you suppress all that, then so all these spin liquids, you get a continuum of excitations, in the inelastic neutrons category. So how this is connected to inelastic neutrons, that also I should say. Okay, so yeah, any other comments so far?
So हम लोग जो मेजरमेंट करते हैं उसमें सैटेलाइट डजंट कम सिमेट्रिक, लाइक अभी स्कैंडियम का कर रहे थे 5/2, तो उसमें वो एक बड़ा और एक छोटा आ रहा है, so that is due to what effect? इसमें तो symmetry.
So there are other things we have not considered. Simple Hamiltonian where the VZZ and VXX VYY are equal. You can have this thing also different. It's divided by something, I think, some asymmetry parameter. So also you can have anisotropy of the hyperfine coupling itself. You know, K is A chi, but the A may be different. You know, it's actually hyperfine coupling tensor. And then you have AXX, AYY, AZZ. So there also you get a powder averaging. So it can be quite complicated. This was maybe the simplest one, where eta, there's no eta, eta is 0. So yeah.
So then, does this somehow, this anisotropy depends on the crystal structure itself, or like? Does it-
Yeah. So because the hyperfine coupling is through these orbitals, and so yeah, it should depend on the crystal structure. Yeah.
Then the electric field gradient would also be influenced by the crystal field.
Yes. Absolutely.
Crystal structure or crystal components?
Crystal
I mean,
structure
the
also.
components inside are creating the field.
But the structure also, no, where are they located?
Like cubic or some
If you have chlorine 1 minus or oxygen 2 minus, of course it will be different, charge is different. But also where it is located. So cubic symmetry side, there is no electric field gradient. So the quadrupole term is 0 because of that. Although there is a quadrupole moment, there is no gradient to couple to. So NQR or even cases where you are able to see these satellites can be good probe of structural transitions. Okay, because something moves, then the EFG will change. Okay, so you should see it as a change of nu q. So actually, the structural order parameter you can track by tracking the nu q. This has been done in cases. Suppose you have people talk about charge order in systems. Charge order. So at high temperature, maybe you have some vanadium just average some valence, and then it charges into vanadium 3 plus and vanadium 4 plus. That will give rise to a change in nu q. I mean, I'm just giving an example, right? If the charges are ordered in some manner, it will change the EFG rather than some average same charge on each one. Compared to that, it will change EFG. So it will change nu q.
तो nu q तो वैसे भी टेम्परेचर के साथ वेरी करना चाहिए ना?
There's a small variation because the lattice contract, so there's a small
So
variation.
अगर वो structural transition है तो it will show some sharp.
It's a transition. It's a phase transition. So other is just a overall variation of the lattice parameters and all, you know. So that's different. So there will be a small variation, often not much. How much crystal changes from room temperature to very
Just
small.
like in heat capacity, we see hum. Similarly, some hum, right? Structural changes.
Sharp change.
Sharp.
It's a phase transition. If there's a first order, second order phase transition, then it's a sharp change in nu q.
I thought some
Hum पर ही
change,
देखते हैं.
change in.
No, it might go.
Maybe a first order sort of transition.
Yeah, it might go like this.
Oh, okay.
Yeah.
Okay, I thought that.
Yeah. It's little like the internal field in a magnetic transition.
हीट कैपेसिटी में भी पाथ चेंज कर लेता है ना, ऊपर से जाते थे नीचे आ जाता है, वही तो थिंग है, हम तो ब्रॉड मैक्सिमम हो गए.
Okay, then so we have this picture of, wait, what time is it? Because that one is wrong. Yeah, another 5 minutes. So we have this picture of nuclear spins. This is the system, and then you have electron spins in the bath. Electron spins are fluctuating, and then giving rise to the relaxation of the nuclear spins between their Zeeman levels. Okay, now suppose, so we are interested in how writing in yellow, so I'll just continue in yellow. Suppose this spin autocorrelation, let's say this varies exponentially. Remember what we have in the integral is something like this, and then there's an integral over time, e to the I omega t. Okay, so if the spin-spin correlations have this exponential decay, where tau c the correlation time, usually considered very small. You have just freely fluctuating spins. So if you have this exponential variation of the spin autocorrelation, then this integral one can work out. Just with the exponential, you'll get it's like 1 over a square plus x square, right? So you'll get a Lorentzian, right? So you get gamma square twice h perpendicular square tau c by 1 plus omega square tau c square. Okay, so it's just doing the integral Fourier transform of the exponential, okay, which is 1 over a square plus x square, e to the minus at is 1 over a square plus x square. Other than, so this just comes out as square of the field, and so there is still no hyperfine coupling because we are not still writing 1 over t1. So once you finally write 1 over t1, this comes out as gamma square, still writing in terms of the h square, tau c by 1 plus omega naught square tau c square. This is called the Redfield formula. So you could write h square in terms of a square s square. Okay. So this is the situation where the spin-spin correlations decay in an exponential manner with time, and then which are these? You have these electronic spins in the bar; they are fluctuating, and it's a autocorrelation. So spin at a site, how its average field is connected to at some earlier time. If that is exponential through a correlation time tau c, then 1 over t1 looks like this. So you can now imagine as so this, by the way, widely used, especially in cases where there is a motion of ions. So at high temperature where there is, so omega naught is fixed in your problem. You are doing, that's the Zeeman, the precession frequency. You are doing an experiment at a fixed field, so the omega naught is fixed. And suppose you are doing as a function of temperature where there is some change in this correlation time with temperature. So at high temperatures there is very weak correlation, very small tau c, but as you come down, this increases, it slows down, the fluctuations slow down, and then you have more component at omega naught and so on. So tau may be variable in some manner, and so there may be features in 1 over T1 versus temperature because of how the correlation time changes with temperature. Okay, so one can get, so related to this, you can look it up. There is a Gloembergen Purcell pound. There is a BPP form of relaxation by which you can track. So if there is some molecular motion which is giving rise to relaxation, then what should be the form of 1 over T1 versus temperature? So 1 over T1 versus 1 over temperature, 1 over T1 versus 1 over temperature, I think goes like this. So when omega tau is very small, then you get a constant. Okay, at high temperatures, let's say omega tau is very small, tau is very small, so you get a constant. Then as tau starts changing, when omega tau is 1, then you will get a very large contribution. So it might go through a peak, and then again at lower temperatures, again when this bypasses that value, again things might change. So I forget now if it is inverted U or this U, but this is all well known. The BPP form arises from this Redfield formula for relaxation. In μSR, by the way, muon spin relaxation is another experiment we do. There also you implant muons which have a magnetic moment, and then look at its relaxation because of local moment dynamics. So there again, this fluctuating fields which are giving rise to relaxation. You use a Redfield-like formula to look at, to find out the electron correlation time. Okay, so this is used in μSR also. There is another form of 1 over T1, which is again used commonly. Okay, so far we didn't write, I'll not write all the steps, I'll write a few steps and then the answer. So, fluctuating field arises from the spins, right? So you have one nucleus seeing many electron spins, each of them coupled with some hyperfine coupling A, right? So you have a fluctuating field arising because of this fluctuating electron spin, okay? And through a hyperfine coupling. Okay, so again, watch out, the dimensions of A, I said there are 2-3 ways to write it. If you write it like this, the A has dimensions of just field.
Yeah.
Okay. In some different ways, it has dimensions of energy, in yet another way, it has dimensions of field per Bohr magneton. So, nominally, it is proportional to the spin. And then, in a different way of writing, so this S is written in terms of its Fourier components, in Q space. Okay, so this is rather written in Q space, and one again works out. You see, the formula for 1 over T1 is the same. You have to take basically square of the fluctuating fields inside the integral, and there you rather write S in terms of Q dependent, and then for A corresponding will be some Q dependent. Okay. Yeah, it's called so the Q dependent A goes by the name of a form factor, but it's basically that, it's a structure related factor, it's a form factor. So again, some algebra which I don't immediately write. What you get for 1 over T1, so the starting formula is the same, this whether through Redfield route or through the Fermi-Golden rule route, you have 1 over T1 is gamma square integral over time of e to the I omega t and times this h plus h minus. Okay, that's the same. Now you're writing the h plus h minus in terms of the spins, but again writing A in terms of the AQ, over Q space. So this is this Moria's way of writing it. And then the 1 over T1 looks like this. So gamma square, so that's the nuclear gamma, minus infinity to infinity, and dt e to the I omega naught t. Remember that was always there. And then you have to write the square of the fields. So that involves now there's a 1 over root n, another 1 over root n from the expressing the spin in terms of its Q component. And then you have a AQ square. So this is the hyperfine field in Q space. So there's a form factor there. And you have S alpha qt, and as it turns out, only you have to do a sum over q, by the way. Only the q minus q survives. Okay. And this is also written as 1 over T1 gamma square over n sum over q aq square s of q and omega. This is what is over here. This is the dynamical structure factor. Okay, so through NMR 1 over T1 measurements, you are probing the dynamical structure factor of your electron system, no? What local moments are there. So this is what is fundamentally the case. The tradition is to write it in a form where you can actually relate it to what you calculate and what you measure, sorry. So using fluctuation dissipation theorem, this S contains fluctuations of the field. So that should be related to chi double prime, the dissipation. Chi is some chi prime, chi double prime. And so this S of Q and omega through fluctuation dissipation theorem is 2 h bar by 1 minus e to the minus h bar omega by kBt times chi double prime Q of omega. Then 1 minus. And then our usual situation is that h bar omega naught is much less than kBt. No, this is very often the case, because this energy you are dealing with is like 100 megahertz and frequency is like 100 megahertz. So what that translates to in terms of energy units compared to you are measuring Kelvin or higher usually. Okay, so you can check. 1 milli eV is 11 Kelvin about. So tenths of Kelvin is like milli eV. 100 megahertz corresponds to how many?
100 megahertz.
So h bar, you can do that. It's much smaller. Okay, so this is almost always valid, and then this reduces to you can expand the exponential and so on. So this reduces to 2 kBt by omega naught chi double prime of q omega naught. Okay, and in this condition, you now put this back in your formula for 1 over T1, and what you have is 1 over T1 equals 2 gamma square kBt by n omega naught sum over q of aq square chi double prime. So this is the one you're often using. So by the way, so what this tells you is that when you do 1 over T1 measurement, what you get is the Q averaged dynamical susceptibility. It's you don't get Q specific, you get sum over all Q values. In contrast, in inelastic neutron scattering, for example, if you have a crystal and all, you can probe at a specific Q. So you get Q specific information. In NMR, you get Q averaged.
So, sir, this Q is what is known as the propagation vector in elastic neutron. We get
Yeah.
propagation.
Yes.
So
Yes.
this is averaged over all the propagation vectors.
Yes. In this case, of course, depending on ferro antiferro, you might have a prominent dominant contribution from some particular Q value. So then that's what dominates. But yeah.
But is there any way to separate those contributions here?
There is not. You measure Q average. Yeah. So that's a sort of downside compared to inelastic neutron scattering. But the thing is, inelastic neutron scattering requires huge facilities, huge costs. This is in a corner of a room, as you already have it. And there you have to then apply a field and maybe temperature. So it's a big effort in terms of technique as well as funds and all that. But yeah, so you measure the Q averaged dynamical susceptibility in NMR 1 over T1. This is not the units we usually write, because remember here this is atomic susceptibility. Okay, and then this also here has units of field. Remember how we did it. Okay, so we usually want to write this in molar units. So, and there's a sum over Q. So, right, this will give you, if you do 1 mole of atom, then the summation will give Na times this thing. So, one has to take care of all that, and then if you take care of these things in our kind of units, what you get is 2 gamma square kBt by Na square of, I'll just write A. So these are different capital A now. Square chi double prime Q of omega naught by omega naught. I'll also put M here to say that this is the molar susceptibility. So you basically multiplied this by mole. To take care of that, there's another N that has appeared here. From N it went to N square. Okay, so here these are in units of, I think I've written it correctly. Yeah, this is in field per nu b units. And this is of course the molar susceptibility. Okay. And you can check, then the unit should come out 1 over second. Okay. So you can sort of verify all that. Okay. Then just because we are almost done with this, so there are a couple of situations where you can reduce the summation further. So if you have these nuclei which are relaxing via some isolated electron spins, isolated moments which are, there's no only weak correlation, some tau c. Then limit of over Q of chi double prime Q omega naught by omega naught in the limit of small omega, which is the case. NMR frequencies are low compared to the other energy scales. This comes out to be, so again in special units, Avogadro number times the uniform susceptibility, temperature dependent, tau by 2 pi, where this tau is the electron fluctuation or correlation thing. Okay, so you suppose this isolated moments vary in a Curie-like manner. Okay, then I have 1 over T1, remember this is 1 over T1. Let's say there is no Q dependence of A. There's no issue of a form factor, it's just uniform. So there's nothing to do in the summation. This reduces to, just in the limit of small omega, reduces to C by T times tau, 2 pi is to take care of the omega. Then the T cancels with that, and the 1 over T1 should be constant. Okay. So there are ways to obtain, so this is available from an experimental measurement or from the night shift. Okay. So, and one can either obtain tau as a outcome of the NMR experiment, or maybe one has some other way to obtain tau. So this is one special case which we often encounter, where you have nuclei and you have some electron moments, which are contributing to this relaxation of nuclei, and then this follows. There is another special case where you have Gaussian fluctuations of the moments. Okay. So then you get this S plus S minus that you write, it has a E S. So the correlation is Gaussian, e to the minus omega square t square by 2. Okay, so remember in the integral we had e to the I omega naught t, and then this h plus h minus. So that you write in terms of the s plus s minus, and the actual form there for the time dependence is e to the minus omega square t square by 2. Okay, if you take the Gaussian fluctuations of these electron moments, then what you get, just the small detail of that I'll maybe write next time. So if you have Gaussian fluctuations, then 1 over T1 works out to root 2 pi a square there is a 3 gamma square, of course, as always, divided by exchange frequency. So for example, you have these different local moments present, and they are interacting antiferromagnetically. So your bath contains antiferromagnetically interacting local moments. Okay? And this omega x is associated with this J exchange by h bar. What is the energy scale of this antiferro exchange between these local moments? Okay. Then the 1 over T1 is given by this, where this exchange frequency is J by h bar root 2 by 3. Actually, if your bath has electron spins, and each spin is interacting with Z other electron spins, then the exchange frequency, sort of the frequency with which these two are fluctuating, is given by this. I can't have it next time, but given by this, and then the 1 over T1, because of these coupled spins, the nuclear 1 over T1 is given by this expression.
So these are special cases.
Yes.
But when you are doing the measurement, how will you know that it's Gaussian fluctuation or normal one? Experimentally, how will we determine which one to read?
So, experimentally we don't know Gaussian fluctuations, but here in the high temperature situation, there's a central limit theorem where you have these random fields, so they have this Gaussian form. Okay, so, but you will have other situations. So you have, for example, exponentially decaying correlation. That was another case. Then in these so-called spin liquids, so the autocorrelation, what is the field at 0 related to field at some time t. a spin-spin autocorrelation does not have the simple exponential form. There is a power law part also to it. Okay, so there's a long time correlations present. So you can have different kinds of correlations which will give rise to a different 1 over T1 or mu SR lambda variation with field, for example. Yeah. But the most you encounter are these Gaussian fluctuations or these exponentially decaying correlations, and then they have these specific forms. Okay, so the one you are looked at currently is this case where you have a Curie-Weiss variation of the bulk susceptibility. So you know you with a negative theta Curie-Weiss. So you know you have this. The negative positive doesn't matter, but you know you have these interacting moments, and that interaction is given by this exchange frequency. And so that is what is, so your spectral function, its component at omega naught is what is giving rise to the nuclear relaxation. Now how that S of Q and omega, that's what we have written down, and finally it comes out to be this very simple expression. So in actual situation, from a bulk susceptibility measurement, so the spin value we know, you're dealing with copper spins in the bath, they're spin half or something else. So this is known. From the structure you know what are the neighbors. Okay, and maybe I should write JEX from some either from the Curie-Weiss temperature, mean field approach, you can, from the measured Curie-Weiss, you can obtain J. Okay, so let's say this is known from susceptibility, so the omega exchange is known, some 10 to the power 14 hertz or something. Okay, that you can put back here, and hyperfine coupling is known from the k-chi relation. So you can estimate what should be the nuclear relaxation. By the way, there should be another one nucleus may be coupled to Z prime electron moments, and if they are fluctuating independently, then you just add the individual rates. Okay, and then this A here is per the hyperfine coupling per magnetic neighbor. Okay, so then this whole thing tells you what the relaxation rate is. And so if you have this only tells you in the high temperature limit. When the correlations between the electron moments are not built up, you are in the paramagnetic limit. As you approach, then this breaks down. Then you have a critical divergence. Then you get large contribution of the spectral function at omega. So what's happening with the fluctuations? As you come down in temperature, they start slowing down. Omega naught is very small. So you start getting a large contribution of J omega at omega naught. So 1 over T1 at high temperature, in the paramagnetic regime, you expect it to be a constant, okay, given by this number. And as you come down in temperature, the spectral function starts having slowing down, and so you get a critical divergence. And ordering temperature, you will get divergence. And below that again, when everything has died down, there are no fluctuations. Where's the relaxation? There's no relaxation. So again, the rate should become very small. Okay, so it's only in this part that this is applicable. Once you deviate from the paramagnetic, then maybe you need to have some models to then obtain this.
So one needs to try to fit with all these special cases and see which is
Yes.
the actual.
Yes. So the exponential correlation, usually when you are dealing with a small amount of local moments in metals, so many different, iron in copper. This was done long ago. So you put 100 ppm of iron in copper, and then look at copper nucleus relaxation rate. Okay, so that qualifies for this exponential decay of autocorrelation, and then a lot of fundamental information you get. This tau will be related to the density of states of the electrons, etc. And so a lot of fundamental information you get. But yeah, I mean, in summary, 1 over T1 gives you information about the electron dynamics, and in some cases you can actually get hard numbers. Okay. So next time maybe I'll just summarize those things in one slide so that it's sort of evident what do you use where. This is, by the way, in our units where you use this in like, I don't know, a straight for newbie or something.
Straight per
Um, what else? There's nothing else.
There nothing. J is in Kelvin.
Ha, J by H bar. So, I mean, this is finally radians per second.
Per second.
There is nothing, yeah. Gamma is gamma, it's a standard unit.
Yeah, J by kb.
No, J is J. Energy units. है ना? J is H bar omega, na? J is energy units. Inside has no units. Energy by H bar. So this is when your spin Hamiltonian, the electron spin Hamiltonian is JSI dot Sj. Okay, then that is what appears here. Because in many cases you will write 2 JSI dot Sj. Okay, then there should be a 2J there. So this is with a Hamiltonian JSI dot Sj that you get a J in this omega Sj.
So this is again in the localized magnetization.
Only, yes. So only when you have local moment. Yes. And in the mean field you can obtain this kind of thing.
So the J sometimes we get in Kelvin, like that J by kb.
J by kb.
J by kb is Kelvin, so accordingly you can use that.
We should use here in energy unit.
The way this is written, this is in energy.
ऊपर वाले फॉर्मूला में भी आ जाता है kb का
H
J by
bar
kb
omega.
यूज करेंगे.
हाँ.
H bar omega is energy. So that's why Jxc is also.
Yes. In formula I think there is somewhere kb.
kb also.
हाँ.
Yeah.
Yeah. So when you have omega, that kb is gone, that's the reason. So you see omega is the denominator, so you will get basically J here.
Yeah.
Okay, this is energy. In your earlier one, you had a kb in the numerator.
Yeah.
Yes.
Okay, so right, you are trying to compare it with this one, right?
Yes.
But yeah, I mean, units have to, you just keep track of units. Okay, you can stop.